Good morning, ladies and gentlemen. My name is Javed Shaban from Karadeniz Technical University in Turkey. This is our second time we are participating to this competition, and we are very happy to be here. Firstly, I want to talk about our design philosophy. San Francisco looks like a sky that is filled with shining stars when viewed from the hills at night, and has always fascinated people with its unique landscape. At the same time, as you know, San Francisco is a shining star in the world of technology. The star-like qualities of the city inspired us to name our building Orient Tower. What is the meaning of Orion? Orion is a prominent constellation located on the celestial equator and visible throughout the world. It is one of the most conspicuous and recognizable constellations in the night sky. So it can be clearly said that the name of the Orient Tower matches the glint of San Francisco City. The Orion constellation not only gives its name to our project, but its geometrical shape has also inspired us in the architectural design of the tower. The longitudinal cross-section between the 15th and the 25th floors of the building was designed according to the geometric shape of the constellation, as can be seen from the slide. The glass curtain wall and triangular segments were used at the facade of the tower to demonstrate the building as dynamic, powerful, and to simulate the shape of the stars. As for structural design, we try to determine a safe and economy system that suitably aligns with our architectural design. In this slide, you can see the structure system. It has 28 stories, and the height of the building is 60 inches. As you know, a total of 25-pound dead load is placed on the building for the shocking tower test. In other words, the building is expected to carry almost 9 times of its own weight safely. When we consider the height of the building and the weight that's coming over it, it can be clearly seen that the building is exposed to a significant shear force. The height of the first and 15th floor is double that of other floors, and because of the maximum shear force that affects the bottom of the building during earthquakes, we are confronted with a soft story problem at the first floor of the building. Therefore, we used shear walls and bracers symmetrically in the building. We used horizontal bracers on the floor to form a rigid flooring. So we tried to provide the load distribution between the structural elements. And we did linear time history analysis with SAP 2000. Due to the highly variable mechanical properties of balsa wood and lack of a design code for this material, it was a bit difficult to evaluate the analysis results. So we paid attention to 2 important parameters in the structure. The first one is to ensure that the maximum shear stress occurring particularly at the ground floor does not exceed the shear strength of the materials. And the second one, we have to prevent the torsional mode of the structure that can cause additional shear stress in the structure. Therefore, we chose symmetrical system to ensure that the building's mass and rigidity center are overlapped. In the construction process, balsa strips and plates were cut by laser cutting machine. After controlling the size of the elements, we started the pasting stage, and finally we constructed our building vertically. After we finished the construction of our structure, we wanted to see the seismic performance of our building by a shaking table, but unfortunately, we didn't have any shaking table, so we were trying to think the ways of testing our model by a shaking table. Our team met. Hassan usually used bike, and the idea that we could do shaking table using the bike had us very pleased. Actually, Hassan got a bit angry, but finally we seized his bike for our purpose. You can see our shaking table in this slide. We used one bicycle, steel rods, chain, steel supports, and the wooden plates and rollers to produce this shaking. Firstly, we disabled the bike And we fixed the body of the bike to the steel supports. And later we used a chain in steel rods to transmit the rotational movement of the pedal to the wooden plate. Thus we have ensured the wooden plate placed on rollers to move back and forth when the pedal is turning. When we tested our model using our checking table and Hassan's effort, it's clear that we cannot get a reliable and exact response values from this test because we can't give a seismic response to the model, and it is depending on the rider's effort, sure. However, we were able to check our building by exhibiting our engineering skills, and we had fun while doing it. And the financial condition of our building is shown in this slide. We calculated the final annual building income as $287,973. Finally, here are my team friends and advisors. Hassan Arslan is a project manager. Hulku Jang, who is not here, is design coordinator. I'm design. Site chief Abbas Jafri, also not here, is site engineer, and building controllers are Serhat Demir and Ayşegül Durmuş Demir. Thank you for your time.
Are there any questions from the judges?
I really like your creativity, both in the architecture and in the testing. That was,
Thank you, sir.
very good. So what gave you the inspiration for the Orion? What gave you the inspiration to use the constellation Orion for your design?
Well, actually, the first one is the shape of the constellation, as we used from 15th to 25th floor. The design of our structure is the same as the constellation Orion. And the next one is that the city of San Francisco is like a shining star of the world in technology or in everything. And that brought us to name our tower Orion Tower.
So with your bike, how did you actually test the structure? Were you just going back and forth with it, or trying to match?
Well, actually, if we would have a checking table test, it would be so good for us, but unfortunately we didn't have. So we just tried to check our table. We wanted to have a seismic record from that, but unfortunately we couldn't do. But we could check our table. Yeah.
Did you do any analysis that showed that you needed the shear walls to extend all the way up the structure?
Well, sorry, can you repeat your question?
So your shear walls go all the way from the base to the top of the structure, right? So it basically looks like it's almost a uniform shear building. Did you do any analysis to justify needing that additional?
Yeah, we did. Actually, at first we used only shear walls and the frames. After that, we saw that the displacement was so big, and the tension stress was the tension stress exceed the strength of the material. We used therefore we added the vertical presses in order to limit the displacement.
Questions from anyone else? Question.
What was the fundamental area of your structure?
It was like 0.095 seconds, like you can say 0.1.
In your constructed model, how did you connect your columns? Are there splice connections, or are they all butt-in connections? How is your structure constructed?
First, we started to build and construct vertically the columns and the shear walls from the first floor, and after that we we came from down to the upper side. I'm not sure if I get your question exactly.
So how do you connect, say, your beam connections to your columns to your shear wall? Are they just butt-in connections, they're just touching, glued together? Did you have to splice any members?
No. We used the glue for the connection of that.
Okay, that was Karadeniz Technical University from Turkey.